The next type of bonding and compound we're going to talk about is covalent. And we said previously that an ionic compound forms when there's a transfer of electrons from one atom to another. So you could say that the electron changes ownership. Covalent compounds form when two or more nonmetals share electrons. And by definition, when you're sharing something, any of you who have brothers and sisters know that I'm not trying to say it's equal, but if you're truly sharing something, no one gets ownership. It's never given completely to one person and taken completely from another. And it's the same thing here with covalent bonding in terms of electrons. So we're going to illustrate this with three different compounds: methane, water, and ammonia. And we'll start by drawing a Lewis dot structure to get a clearer look at what we mean by this sharing. So we start with a carbon at the center and 1, 2, 3, 4 valence electrons around the carbon, which means in order to achieve a full octet, 8 valence electrons, it already has 4. Carbon needs 4 electrons. So that's why you see 4 hydrogens around the carbon. There's hydrogen with its 1 valence electron. Here's another, a third, and a fourth. And what you'll notice is that if neither carbon nor hydrogen gain or lose electrons, but instead they share their valence electrons, then carbon gets ownership, at least partial ownership, of 1, 2, 3, 4, 5, 6, 7, 8 valence electrons by forming 4 covalent bonds with hydrogen. Hydrogen only needed 1 more electron in order to complete a full valence shell and have a duet instead of an octet. And you can see each hydrogen has 2, at least partial ownership of 2 valence electrons. So both carbon and all 4 hydrogens are able to attain a full octet, a full valence shell, by sharing their valence electrons. And when we do the same thing for water, we start with the central atom, which is oxygen. It has 1, 2, 3, 4, 5, and 6 valence electrons, surrounded by 1, 2 hydrogens, each with 1 valence electron. Again, just like the previous example, you see 1, 2, 3, 4, 5, 6, 7, 8 valence electrons surrounding oxygen now. By sharing a valence electron with 2 hydrogen atoms, oxygen gets a full octet. And the same thing happens as it did in the previous example with hydrogen. By sharing 1 valence electron with oxygen, each hydrogen gets a full valence shell. And our last example is ammonia. So we start with nitrogen and 1, 2, 3, 4, 5 valence electrons surrounded by 1, 2, 3 hydrogens, each with 1 valence electron. And you look, count them up: 7, 8 valence electrons around nitrogen. And again, each hydrogen has partial ownership of 2. So both atoms, or all 4 atoms in this case, end up with their full octet. Now, a brief review of ionic versus covalent to summarize. There are 5 different scenarios, and we're just talking about the bonding between a metal and a nonmetal, a metal and a polyatomic ion, two polyatomic ions, and then 2 nonmetals. We're not talking about within the polyatomic ion, which we'll get to later. So between a metal and a nonmetal, that's our first and our simplest ionic scenario. A metal and a polyatomic ion is also ionic. The bond between a nonmetal and a polyatomic ion is ionic. And our fourth ionic scenario is 2 polyatomic ions. So the only scenario in which a covalent bond is formed is when you have 2 nonmetals. And then last up, just want to talk about the metals in general as pure substances that we find to the left of the staircase. And the fact we said that they conduct electricity, I want to reiterate the idea that this ability to conduct electricity is based on having what we referred to as a sea of mobile valence electrons. The key being the last part. The C is just to give you an idea to help you understand that it's wave energy, that it's conducting, but these mobile valence electrons that are not possessed by any one individual metal atom allow electric current to move through metals. And if you check this animation out, it's really good. I suggest you click on it. It'll just give you an idea of visualization for what it means to have those mobile valence electrons, and it illustrates what it looks like to sort of conduct that alternating current.